Yeah, so there's an obstacle on the way. You choose the L to be too big. Let's say you chose the L to be so big that it ended up at the end there. Then you like skip all the steps in between, right? And so there's a bit of a tuning process in choosing the L, which both continues to make progress while doesn't skip through large parts of the trajectory that were chosen for a reason, right? Like there's a reason I didn't just teleport from the start to the end. I like went around that path. And so you don't want to pick points that are too far away. And so there's a bit of tuning you need to do for that. Okay, so now we've said we've chosen a reference point. The next thing you want to do is you want to compute the error to the reference state. So you've chosen a point, whether it's the closest point or a look ahead point, or you've chosen some point on the reference trajectory, and you want to like figure out how to get to that point, right? So you want to figure out the error between your current state and that state, and you want to figure out how to minimize that error, right? And so what you want to do is you want to measure the difference between your current state and the reference state. Actually, this is your current state. That's the reference state. You want to figure out the error between them, right? And so the error can be decomposed into two elements: the along track error, the cross track error, and the heading error, right? So if you think of this as your x-axis, this is your y-axis, right? The along track error is the thing that's along the length of the car. The cross track is the thing that's perpendicular to the car, and the heading error is the change in orientation, right? And so you want to kind of minimize a combination of this along track error, cross track error, and heading error, depending on what you can control, right? So for instance, if I can only control the steering angle, but I can't control the speed, then I can't really reduce the along track error, right? So they can't like slow down my car. So if I can only control, let's say, the steering angle, then I can only reduce the cross track error. And so these terms don't really matter that much. They're just an easy way to understand that a long track error is like what's your error along the direction of motion. Cross track is what's the error along the direction, like lateral direction, and heading is like what's the direction, what's the error in my orientation. Right? Okay, so you computed the error by subtracting. You compute the error by taking your current XY theta, and you really want to subtract out the reference point so that you get the along track error, the cross track error, and the heading, right? And we're going to try and figure out how to compute these things. So one thing we're going to need as a piece of machinery before we compute these errors is the idea of a rotation matrix. How many of you all know what a rotation matrix is? Natalie? Okay, we'll go over it real quick. But the idea is if you have like two different frames of reference, right? Let's say you have the frame of reference A and the frame of reference B, right? So frame of reference, they're both in the plane. One of them is just rotated theta degrees, right? What a rotation matrix does is it allows you to take a point in the frame of reference B and convert it into a point in the frame of reference. And so let's say you had a point x comma y in the frame of reference B. You can multiply it by this thing called the rotation matrix to put it into the frame of reference A, right? And so the way I like to think about it is that, let's say you had, I guess here we're going from B to A. So let's say you had some point, or call this X in frame of reference B, and then you had a rotation matrix that takes you from B to A, right? So then this gives you X in the frame of reference A, right? And so the rotation matrix lets you rotate points along, along different orientations. And so rotation matrix is typically given by something like this. Except the angle is theta, the rotation matrix is cosine minus sine, sine cosine. And I always get a little bit confused on like the signs here, which direction is theta. But you could just solve this with simple trigonometry, right? So you can say that like an easy way I find to do it is like, if you look at this particular thing, take the point 1, 0 in frame of reference B. And in frame of reference A, it's basically its position going to be cosine theta, sine theta. And then you can try and figure out the sign of the rotation matrix accordingly, right? But the general point to remember is that if the angle of rotation between the frames of reference is theta, that is your rotation matrix. And to rotate a point, you just take its x and y and multiply it by the rotation matrix, right? Okay, so what we want to do is we want to try and re-express the error in the frame of reference of the we want to re-express it in the frame of reference P of the car, right? So we have an initial error, which is the difference between your current position XY and your reference position, right? So you have like X and Y here, you have the reference position, you have the difference between them, right? And you want to like reproject in the frame of reference of the car. So all you're going to do is you're going to multiply it by the rotation matrix. You have frame of reference in A. So the difference, so the problem is that A is like kind of in the global frame of reference, right? You don't care about the global frame of reference, you care about the frame of reference of the car. And so what you're going to do is you're going to like, this is the global XY coordinates. You're just going to rotate it so it matches the car's coordinates. Right? So you're going to say, let's take the error in the on the global frame of reference, and let's just rotate it so that it matches the frame of reference of the car. Right? And so all you're going to do then is you're going to say, let's take the error, right? This is just the error. The difference between XY and X reference, Y reference. And you're going to rotate it so that it matches the frame of reference of the car. Right? Just multiplied by the rotation matrix, and that's going to be your error. Does that make sense? So the problem with just doing it without the rotation matrix is that the straight, like, you want to do everything in the egocentric frame of reference, like your car is only egocentric, right? And you want your error to be in the egocentric frame of reference, not in the world frame of reference, because you don't care about it. Right? So this doesn't really matter that much, but it's just like a nice thing to know. And then your heading error. So what I did so far was an error in X and Y, just re-expressed in the frame of reference of the car. And then the heading error is just the difference between your current position and your reference position. Right? That's it. And so we've computed, these three terms, the along track error, the cross track error, and the heading error. Right? These are just like expansions of that rotation matrix times the error. You can just work it out, but kind of gives you the same thing. But intuitively, you just want to take the difference of points, reproject it into this frame, that gives you the error. And your goal and control is to just try and minimize this error, right? So all that the control law is going to try and do is it's going to try and design this rule, right? Which is going to take in your current state and your error, and then try to output an action that tries to minimize this error. Right? And so the goal of all control theory is really just to figure out what this control law is going to be and provide us some guarantees that this control law is going to work. Right? And so what we'll cover in the next few classes is a bunch of different techniques in order to reduce the error. We're going to have PID, pure pursuit, MPC, QR. And then we'll see if we have time for more, but the idea is just to find different ways to express this case. Okay, hopefully that makes sense. Sorry about the technical issues, and have a good weekend.